back to Science Fantastic with Professor Michio Kaku. Every week on Science Fantastic, we explore the incredible developments that affect your life and affect your view of the universe. And today in this hour, we're going to take your listener phone calls. That's right, because this hour is your hour. Okay, let's take the first listener phone call.
Dr. Kaku, I am Jim, Charleston, West Virginia. The radio station is WCHS. My question is that in your book, Physics of the Impossible, you indicate that the closer an object travels to the speed of light, the flatter it gets and the heavier it gets. And I wonder why that is. Thank you.
Well, when you discuss relativity theory, everything we know about common sense goes out the window. Common sense says that if you weigh, let's say, 150 pounds, and you travel in a car, your weight doesn't change at all. You're still 150 pounds. Whether you go up, down, sideways, 150 pounds is 150 pounds. And your size and your width remains the same. Your body shape doesn't change just because you're in a car. Well, along comes Einstein, who says that all this is wrong, because the speed of light is a constant, no matter where you look, no matter how fast you go. But you see, common sense says that there's nothing special about light. You can go faster than light just by hitting the accelerator. Wrong. Einstein came up with this revolutionary idea that the speed of light is unique in the universe. It is the ultimate velocity. But you see, if the speed of light is the ultimate velocity, that means that everything we use to measure space, time, length, width, everything we know has to be altered just so that the speed of light is constant. So in other words, let's say you're in a jet airplane and you have a laser gun, and you hit the laser gun on the jet plane. You would assume that the laser light is boosted by the speed of your jet. Nope. The speed of light is the same no matter which way you travel. Amazing. So if that's true, that means that everything you measure, your measuring sticks, your clocks, also have to be changed. And it turns out that your shape is flattened the faster you move. You become a pancake as you approach the speed of light, and you get heavier. Now, how much heavier do you get by traveling at a certain velocity? Well, the energy of motion has turned into mass to make you heavier. That's where the mass came from. It came from the energy of motion. Well, how much energy of motion turns into how much mass? Well, it's one line, E equals mc squared. In fact, that's how Einstein derived that equation, by calculating how much heavier you are by speeding up in a rocket ship. E equals mc squared is a direct consequence, a one-line consequence of the fact that the speed of light is constant no matter which way you move. Now you may say to yourself, well, this sounds stupid. I mean, come on, give me a break, right? No. If you don't believe me, look at the sun. Why does the sun shine? Precisely because the mass of hydrogen has turned into E, sunlight. And why do we have atomic bombs? Why do we have hydrogen bombs? Precisely because the mass of uranium and hydrogen has turned into E energy. So this simple observation that the speed of light is constant no matter which way you go, that simple observation unleashed the atomic age. That's why we understand what makes the stars shine. That's how we understand what makes nuclear weapons. Why do we have nuclear power plants? Because E equals mc squared, which in turn is a one-line consequence of the fact that the speed of light is constant no matter where you go. Amazing. Violates common sense, but hey, Mother Nature does not care about your common sense. Sorry about that. Okay, well, let's move on to the next listener phone call.
Yes, my name is Joe from WILK in Wilkes-Barre, Pennsylvania. And my question is, does a spinning top have a different weight on a scale when it is in motion or at rest? And depending on that answer, would it matter if the middle of the top was filled with a liquid. Thank you, Dr. Kaku.
Okay, well, if I have a top and I spin it, the weight does not change. Now, of course, if you spin it close to the speed of light, then we have to put in relativistic corrections. But at ordinary velocities, if I spin a top, the weight remains the same. Now, let's say I put a liquid in that top. Same thing. It remains the same. And so the weight of a top does not change. However, if you accelerate the top in a forward direction, then the weight does change. Welcome back to Science Fantastic with Professor Michio Kaku. This hour is your hour. Well, before the break, we had a question about a spinning top. Does it get heavier when you spin it? And the answer is no. However, when you start to reach the speed of light, that's when things begin to change. So if you were to take that top and throw it in a straight line, it would get heavier. Now, you may say to yourself, well, that's crazy. Things get heavier the faster you move. And the answer is yes. Let me tell you a little story. When I was a grad student at Berkeley, University of California, Berkeley, so many years ago, we heard a story about the fact that there was a cyclotron with a huge magnet that was built on the Berkeley campus by Professor Lawrence. Well, Lawrence was of the old school. Ernest Lawrence said, bah, humbug. Einstein can't be right. A rock is a rock is a rock, no matter how fast you throw it. And so he built this huge magnet to build a cyclotron to speed protons in a circle without relativity. He did not put into relativity into his equations. Well, they turned it on, and what happened? It didn't work. It was this gorgeous, gigantic magnet, and it did not propel protons correctly. It was a huge waste. Well, along comes World War II, so they used that magnet to enrich uranium, which of course does take advantage of relativity. So here's the irony, that we have a Nobel Prize-winning physicist, Ernest Lawrence, who did not believe in relativity. He designs this huge atom smasher, and it doesn't work, because protons do get heavier the faster you move. And so they had to junk it, but then along comes World War II, and they had to use the magnet precisely according to Einstein's theory of relativity. So that's the irony, that you can deny relativity as much as you want because it violates common sense, but the universe may not necessarily believe or care about your common sense. Okay, let's move on to the next listener phone call.
Lance Sanders calling from Corpus Christi, Texas. So, if we're living in a three-dimensional universe with a fourth temporal dimension, why can we move through the three-dimensional plane but not move throughout the temporal dimension in multiple directions? That's my question.
Well, you ask a question that goes to the heart of relativity. You're right. Time is the fourth dimension, but it is the fourth temporal dimension, meaning that it is a little bit different from the other three directions. For example, when you're in elementary school or high school, you learn the Pythagorean theorem, that a squared plus b squared equals c squared for a right triangle. So if I have a right triangle with sides A, B, and C, the relationship is given by a squared plus b squared is equal to c squared. So the two dimensions of space, length and width, are pretty much the same thing. You can move left, right. You can move forward, backward. No problem. But you see, when you start to put in relativity and you start to put in time, there's an extra minus sign that emerges in that equation. So you get a squared plus b squared minus t squared equals c squared. Now, what does that gibberish mean? It means that time is the fourth dimension, but it is not exactly like the other three. There's an extra minus sign in that equation, And if you try to move now, because of that extra minus sign, it does not allow you to go backwards. Now, you may say to yourself, well, gee, that's kind of a real downer, but that's the way special relativity is. Special relativity says that time is the fourth dimension, but you cannot go backwards in the fourth dimension because of that extra minus sign. Now, when you start to go to general relativity, then a squared, b squared, t squared become curved. Then you can start to go backwards in time. But that requires a black hole. So in other words, don't expect anyone to go backwards in time anytime soon. You would have to, according to Einstein's theory, have energy comparable to a black hole to take advantage of the general theory of relativity, in which case a squared plus b squared minus t squared are curved in the fourth dimension, making time travel possible. So in other words, don't get your hopes up. Okay, let's move on to the next listener phone call.
Dr. Kaku, this is Stu listening to you on KFQD in Muldoon, Alaska. I heard you mention that a gyroscope inspired Einstein in some ways. I remembered what a gyroscope was kind of from a class I had, but I looked it up again. Could you explain to everybody why a gyroscope exists and why it inspired Einstein? I imagine the wheel in the middle continues turning regardless of how the stand is, if I remember right. That comment you had was very interesting. Could you please explain it in detail? Thank you.
Okay, well, I've interviewed a lot of Nobel Prize winners in the past, and I asked them, when you were a child, what was it that set you off in the direction of eventually becoming a scientist and winning the Nobel Prize? Well, different things inspire different people. I asked Steve Weinberg, who is the founder of modern quantum field theory, and he said that when he was in high school, or junior high school, it was a chemistry kid. He loved playing with chemicals, but then he realized that what makes these chemicals work are atoms, so then he got interested in physics as a consequence. Isidore Rabi helped to build the atomic bomb, and he got interested in science by reading an astronomy book and realizing that there are other worlds out there that he couldn't see, but obviously exist. And for my friend, the late Heinz Pagels, it was a visit to the Hayden Planetarium in New York City, opening his eyes to a whole new world. And for Einstein, it was playing with these little toys, compasses, gyroscopes. Why did they fascinate him? Because he began to realize that they were forces that you could not see, that were invisible, but made things work. A compass needle, for example, spins, but you cannot see magnetism. Magnetism, of course, does exist. You can play with toys. Electricity does exist. But electromagnetism is not visible until it's in the optical region. But infrared, ultraviolet, they're outside the range of the human eye, and they're invisible. So he was fascinated by the fact that what you see is not necessarily real, that they are unforeseen, unseen forces that can determine the way things are. So if I have a gyroscope and I simply drop it at one point, it doesn't fall. It falls to the side and then begins to process in a circle, a horizontal circle. And so he began to realize that common sense is misleading. Common sense is only based on observation, but observations can trick you. And so he realized that a gyroscope obeys forces that are beyond the forces of common sense. And the same thing with a compass needle, that what moves the compass needle is something that's invisible, you cannot see, but is obviously there. And so some people say that, what is science? Science is what separates us from common sense. Common sense is your first impression, because it's based on what you know in the past. But your first impression is not necessarily real. It's only an approximation of what is real. And the same thing as I mentioned with relativity. when you approach the speed of light, you get heavier and you get flatter. That violates common sense. But that's because we rarely accelerate toward the speed of light. I mean, how many times do we travel at 186,282 miles per second? Never. And so our common sense is only an approximation to reality. And that's where science comes in. Science is the difference between reality and common sense. To Science Fantastic with Professor Michio Kaku. In this hour, once again, we're going to take your listener phone calls. Okay, let's move on now and take the next listener phone call.
Hi, Dr. Kaku. My name is Tim, and I listen to you regularly on 98.7 Keys in Corpus Christi, Texas. My question is this. I'm a religious person. I'm a Christian, but I also, know that the mysteries of this earth are designed to be solved through science. But my question is, in your career, how have you explained the relationship between religion and science? Because I don't believe that they are just inherently opposite. I'd love to hear your take. Thank you.
Mm-hmm. Okay, well, let me give it a try. Galileo, several hundred years ago, was asked that very same question when he was put on trial for heresy. And his predecessor, Giordano Bruno, was actually burned at the stake, burned alive in the streets of Rome for talking about the possibility of life in outer space. And so they told Galileo, under pain of death, they said, remember what we did to Bruno? We burned him alive. And they demanded that Galileo recant what he talked about science. So what was Galileo's response? Well, in a letter, he says that the purpose of science is to determine how the heavens go. The purpose of religion is to determine how to go to heaven. So in other words, they're complementary. In other words, science is about natural law, the laws of nature that we see around us. That's what science is all about, to try to understand and explain and maybe harness the laws of nature. While religion is about ethics. It's about how to be a good person. It's about treating others like you would have them treat you. It's about how to behave. It's about how to go to heaven. So he didn't see any direct contradiction between science, which is the science of natural law, and also religion. Now, this debate, of course, is not just confined to the Renaissance of Europe during the 16th and 17th centuries. It's universal. Every society has to come to grips with this. For example, take a look at the Muslim countries 1,000 years ago. Well, let's take a short commercial break, and after the break we're going to continue a discussion of the relationship between science and religion. Welcome back to Science Fantastic with Professor Michio Kaku. This is your chance to give us a call and get online. Okay, well, before the break, we had a question about the relationship between science and religion. And I mentioned the fact that, well, if you were a Martian and you were to visit the Earth 1,000 years ago, which nation do you think would rise up to dominate the planet? Well, if you take a look at what happened to Europe, you would say, nah, no way. The Europeans were involved with the Inquisition, burning witches and burning warlocks and heretics. And take a look at China. China was rising with the invention of the compass, writing, the printing press, gunpowder. And look at the Muslim nations. They had algebra. Al, of course, means the in Arabic. Algebra is an Arabic word. Look at the names of the stars, Algol, Altair, all Arabic. So when the Roman Empire fell apart, which civilization carried on much of the knowledge of the Roman Empire? And that is the Arabs and the Muslims. And then the question is, if you were a Martian landing on the Earth, which nation do you think would rise? Well, you'd say, hands down, China and the Muslim countries, because of the fact that Europe is mired in inquisitions and burning witches. But what happened? What happened then was there was a debate, a long-standing debate within the Muslim countries about science and religion. There were some people who said that we should not study science because Allah could change nature any time He wishes. Just with a stroke of a pen or with a nod, all of a sudden the laws of nature can be changed, so it's worthless to discover natural law because they can be changed by Allah. The other side said no. Natural law glorifies Allah. It shows you the beauty and the elegance of the laws set into motion by Allah. Therefore, we should study Allah because that's His word. Well, what happened was, over the centuries, the first group gained sway over the Arabic Empire. And so science became a secondary, tertiary consideration, relegated to the back rooms, and all that knowledge gradually fell into disuse, and that began the decline, the gradual decline of the Muslim Empire. While Europe, after 1,000 years of darkness and burning witches, after 1,000 years of inquisitions and show trials, they finally began to realize that, hey, maybe natural law does have something to say about the universe. And so Martians 1,000 years ago, landing on the Earth, would have to revise their opinion, because ultimately the nations of the world which rose to the challenge were those nations that embraced science. The Chinese, by the way, had a similar debate. In the 1400s, they had a huge fleet of ships that sailed the ocean blue, went all the way to Africa, and was basically looking for potential rivals to the Chinese Empire. Well, they couldn't find any, and so according to legend, the Emperor of China, discouraged that his fleet of ships could not find anything useful, burned the boats. The largest fleet of ships for the next 300 years was burned to the ground and fell into disuse because the Chinese said, there's nothing out there. We're number one. Well, you're not number one forever. And so the lesson I'm trying to raise is simple. Science is about natural law. Do you want to use natural law in order to create prosperity, raise the standard of living of people, educate people to the way things are? Or are you going to get mired in obscure religious conflicts about how many angels can dance on a pinhead and things like that? And so the nations of the world which rose to the challenge are those nations which embrace science and technology. To Science Fantastic with Professor Michio Kaku. Okay, moving on. Let's take the next listener phone call.
My name is Joyce. I listen to WCHS, and my question is, what is a star made of, and how far away is the closest one? Also, are the ones we are seeing really burned out?
Okay, well, let's talk about stars and the nearest stars to the planet Earth. First of all, we know almost everything about stars, and how do we do that? Well, we look for indirect signals from stars called sunlight. If you take sunlight and run it through a prism, you get a rainbow. This was shown by Isaac Newton hundreds of years ago. But if you analyze the rainbow very carefully, you can find lines, black lines, that are the fingerprint of chemicals inside the sun. And so when the electrons dance inside an atom inside the sun, it releases a rainbow with certain lines inside, and by identifying the lines as like a fingerprint, you can identify the chemical composition of what causes the sunlight. We also see this on CSI television. When a crime is committed, like mud on somebody's shoe, and you want to know where the mud came from, you heat up the mud until it fluoresces, you run the light through a prism, and the prism then reveals these lines which then say, bingo, here's oxygen, here's hydrogen, here's nitrogen. So when you do the same thing for the sun, bingo, you find out the sun is made out of hydrogen. And then there's another element there called helium, which was actually first discovered in the sun. Helium is a rather very rare element on the Earth. So scientists found there was this contaminant in the sun, this new substance discovered in the sun. So it was called sun metal. Helium means sun metal. Now we know, of course, that helium is not a metal, it's a gas, so they made a mistake. But the name stuck. And so when hydrogen burns at a very high temperature, millions and millions of degrees, it fuses to release energy by E equals mc squared, and that's why stars shine. Stars originally are maybe like a light year across in dust. Gravity begins to compress this dust cloud. The dust cloud begins to spin, and in temperatures, as temperatures rise, as the dust cloud is squeezed, and it reaches 10 to, let's say, 100 million degrees, then bingo, it starts to fluoresce. Now, the closest star to the Earth is the triple star system, the Alpha Centauri system. 3 stars that are about a little over 4 light years away. So it would take over 4 years for light to go from the Earth all the way out to the Alpha Centauri system. And, believe it or not, we now know that one of the stars in this triple star system is Earth-like. And that's causing a lot of excitement, realizing that the closest star to the Earth, that is the Alpha Centauri system, has Earth-like planets that maybe, just maybe, we might be able to visit. There's a program called Breakthrough Starshot, backed by billionaires, and they want to build the first starship. Not the way you see it on Star Trek. No, they want to make tiny little computer chips, boost them to near the speed of light by shooting laser beams at them, and having these computer chips by the thousands then race toward Alpha Centauri. Each chip has a radio and a sensor, and as it approaches the stars, it radios back the information to the Earth. So here is a way in which we might be able actually to have the first starship just within the next, who knows, 50 years. And it's being backed by billionaires who really want to know what's out there. And so, yes, we do know quite a bit about stars. In fact, when I was in grad school at Berkeley years ago, my roommate was an astronomy major, and he would actually, quote, put a star in the computer in the morning and have the computer evolve the star using known equations, and by the afternoon, he could see how the star survived its life history. So in other words, we know almost everything about stars. Okay, let's move on and take the next listener phone call.
Hi, my name's Bruce Vogel, calling from Fairbanks, Alaska, on KFBX, and I would like to know if they've figured out where on the globe the moon was taken out of when it separated from the Earth. Thank you very much. Enjoy listening to you.
Okay, well, the Earth and the solar system is about 4.6 billion years old. Now, the moon, we think, was blown out of the Earth about 4.1 billion years ago, when an asteroid about the size of Mars plowed into the Earth and then hurled a huge chunk of the crust and the mantle of the Earth into outer space. Eventually, that chunk of dirt in outer space coalesced to give us the moon. Now, there's a debate among geologists as to exactly where this took place. What was the angle of the impact? We think that the collision was not a direct hit. It was a glancing blow. And we know that by looking at the chemical composition of the Earth and the Moon. Believe it or not, Moon rock is almost identical to Earth rock. Because, of course, the Moon came out of the Earth. But exactly where was the impact? We don't know. Okay? There's many theories about that. But that is a big mystery that I would like to know exactly where the Moon came from when it was blown out of the Earth about 4.1 billion years ago. Well, unfortunately, we have run out of time.